Hello, today I'm going to talk about the how to select models or polynomial orders in linear regression, and I'm going to try to combine it with the concept of R-square. And this talk is going to be a kind of continuation of the concept of assumptions, how I treated the subject. So for those who have not watched that presentation or who haven't been available to the presentation or the online presentation, I highly recommend you to watch the corresponding YouTube video. Although the whole thing about assumptions may sound a little bit boring at first, the general approach will still be applied in selecting the model order, the polynomial order in linear regression, and it's actually the concept of assumptions, how to apply them in, especially in statistical sciences, is a much more general subject or a vast subject. So it's a good idea to watch that video before watching this current one. Anyway, so today's talk will be about, as I said, how to select polynomial order in linear regression, and I'm going to try to combine it with R-square. First of all, very briefly, I would like to talk about the concept of linear regression. Here, what does linearity correspond to? Here, actually, the linearity corresponds to parameters. So our typical simple linear regression equation is as you can see, is this one. Now, when you put it a second order polynomial term, x squared, still this is linear. Why? Because actually this is in linear regression, we mean linearity with respect to parameters. So basically the parameters are beta 0, beta 1, beta 1, 1 here, and they are all linear. This regression formulation is linear with respect to these parameters. An easier way to see this is, instead of x squared, you may equate this x squared to another variable, another independent variable, call it u. So basically then this whole equation can be written as y regressed on x and u. And x and u will be multiplied by two parameters, and it's very easy to see that the resulting equation will be a linear regression model. Well, it's going to consist of two independent variables, as you can see. Well, x and x squared, they are not independent with each other. They are independent with respect to y it means. Anyway, so it's not going to be a simple linear regression formulation. It's going to be multiple linear regression formulation, but still it is linear regression. Still, this is another linear regression equation, although the square root may seem awkward at first sight. Using the same logic as I've used it for this one, instead of square root of x plus 1, you can equate this to another covariate. Instead of independent variable, let me call covariate or predictor. You can equate u to square root of x plus 1, then you can regress y on u, and it's going to be a simple linear equation, linear regression equation, as you can see. And this can go on forever. This is also another linear regression equation, because instead of sine x, you can equate this to another variable. So these are all linear regression models that we can handle within the scope of this course, as I said. So one may tend to think that using this logic, you can make any equation linear. Unfortunately, that's not the case. If I give a statistical model such as this one, there is no way to convert this equation because x plus beta 2, you cannot equate this to another variable because we do not know beta 2. So therefore, this equation is nonlinear with respect to parameters. So it's not important that we have square root of x here. We have square root of beta 2 plus x here. This square root beta 2 is the problematic one. And another one, which is pretty much frequently seen nowadays because it's related with exponential growth, is this equation. Well, there are some methods which are usually named under the name of linearization, and especially you are going to see some of them. Maybe you have already seen them in reactor course, the relative with reaction order. But from pure statistical point of view, this is a nonlinear regression model, which is not very straightforward to solve, I may say, and this is out of the scope of this current course. Anyway, So what's the big deal about linear regression models? Because when you have a linear regression model, you can easily solve it by least square formulation. We have only covered for simple linear regression where you have a single independent variable in statistics course and also in laboratory course. Nevertheless, I can assure you that it's very easy to generalize it to any number of predictors, covariates, or independent variables, as long as the whole thing is linear. So there is one thing that we haven't talked about yet in statistics course and also within the scope of this course. It is which of the linear regression model, actually, if you just extend it, which any model among the whole infinite number of members constructing the whole functional family, but for the specifics of this course, we are talking about linear regression models. Still, we have an infinite number of linear regression models. As you can see, these are just polynomial models. You can make them square root, you can make them sine, cosine, any other nonlinear transformation on x, but still linear with respect to beta. You can put it in any form. So we are going to have an infinite number of functions in a function family, I may say. So which of these equations will be valid for our data at hand? This is a topic we have never talked about, and actually this is not an well, actually I said this is an easy question. No, this is not an easy question. I'm sorry for this mistake. This is not an easy question, and this has been a topic of statistics and machine learning for quite some time, for which we don't have a very clear. Well, we have many methods, but there is not the definite perfect method here. But this, within the scope of this presentation, we are just going to scratch the surface and see what's going on. So the approach we are going to follow is going to be based on the concept of assumptions that I have already talked about. And this is a very general method in all statistical sciences. So what we do here, now let's combine the concept of assumptions with what we are doing right now. Since we have an all infinite family of functions, we choose one of them at the beginning. Now that is a difficult question to answer. For instance, which one of these are we going to choose? Let me give you the answer that way. The simplest one that seems feasible for, or that seems possible for the data at hand, I may say. So you choose the simplest model. Let's say that this is the simplest model that seems to fit to the data. You start with this model. Then you check, after you model your data, you check whether the model fits the data. And we're going to talk about how to make this check. And if the model, the model predictions or the model fit seems satisfactory with the experimental results, then we say the assumed model is valid. As I said also, I think during the presentation, we do not say the model is true. We do not say the model is correct. We just say that the assumed model is valid because given some much more data, future data, the validity of the model may be violated. Later, we may feel the need to change the model. So there is almost never in statistics a perfect model that's going to be applicable for all cases. So validity for the data at hand is pretty much the sufficient end that we need to reach. However, if the model that we fit does not seem valid, and as I said, I'm going to talk about the test that we are going to apply for this purpose, then we go back and change our assumption. We usually make this equation slightly more complicated to fit the data, or we just change a couple of things in our model so that the assumed model is going to fit to the data. So this whole iteration is repeated until we reach a valid model. So that's the general approach. But as you can, I hope you remember from the concept of assumptions, there were a couple of examples I tried to explain. For instance, the density of air, the constant density of air assumption. We may check the validity of the assumption. You don't need to wait until the very end of the whole analysis and the experiment. You may check, at least to some degree, the validity of this assumption at the very beginning. You may examine the operating conditions, how much pressure is likely to change, how much temperature is likely to change. Then you may check the theoretical consistency or the validity of the constant density assumption by seeing how much density is likely to change within that range of temperature and pressure, and then you may continue. If the pressure changes seems to be small, then constant density assumption seems to be a better approach. Then you do the whole thing, you do your analysis, and then check whether the model fits the data or not, the same thing. But you may check the validity of your assumption at the very beginning. And this is usually what we also do in statistical modeling. During the early stage of forming our assumption, we may check the validity. A couple of typical examples. If, for instance, we have a theoretical expectation that we have a minimum or maximum in our data, then it is not a very feasible or a very plausible way to use a first order polynomial, because a first order polynomial is going to increase or decrease all the time with no maximum or minimum. So it's not possible to fit, to give a good fit for a system with a maximum or minimum using a first order plot. Or more than theoretical expectation. This is the first example was just before collecting the data. You collecting the data and your initial analysis seems to say that there seems to be a curve of the response variable or in the dependent variable with respect to independent variables or covariance. So in this case, again, using a first order model does not seem to be a good idea, because as I said, as you can realize, and as I said also for the first example, a curvature cannot be fit using a first order model. A very typical example may be the pump efficiency versus flow rate relation. Maybe you have seen in fluid mechanics course, but you are going to be pretty much interested in this relation in your design course on the 4th year. Anyway, so the theoretical expectation is that the pump efficiency usually has a maximum about a certain range of flow rates. This is our theoretical expectancy from fluid mechanics. And let's say that this data or these different types of data are collected under different conditions. So both the theoretical expectancy and also the experimental data shows that there seems to be a curve in our data, and it seems to be especially a single maximum point. Therefore, it is not a good idea to start to assume a first order polynomial for this case. The simplest model to assume for this specific experiment seems to be a second order polynomial. Why? Because mathematically, second order polynomial is going to have a maximum or a minimum. Therefore, that second order polynomial might, it doesn't need to be, but it might explain this curvature. So it is a good idea to start using the second order polynomial for this specific case. But if you are, for instance, talking about a calibration curve, and if you have reason to believe that a first order response is to be expected for this calibration curve for, let's say, concentration, conductivity versus concentration, or concentrations versus conductivity, just go back to the calibration chart lecture, it might be both of those. So anyway, if you have a linear trend that you are expecting, that it's a good idea, or it's the best idea to start with a first order polynomial. Anyway, so let's generalize this whole thing. Let's say that we don't have a theoretical expectation of the model and we just assume a first order polynomial. So if you don't, as I said, if you don't have a theoretical expectation, and if your data does not say much about what's going on, and in some cases it may not be easy to see how data is scattered if you have many different covariates, I may say, then a first order model polynomial is the simplest and also the most practical and reasonable first assumption. You start with this one. Then the question is, how can you assume or how can you verify the validity of this model? you model the whole thing, and then you use something called residual analysis. Now, at this point, I should point out it's not R-square that you may be somehow accustomed to, or you might have heard this R-square to be a good thing. So it may be used in modeling or in choosing the valid model here. That's not the case. So to choose the valid model among a family of functions is performed by using what we call residual analysis in statistics. I'm not going to talk about the whole residual analysis, but it's going to be a kind of the fundamental idea, and it's going to be a kind of practices that you can use in your reports for the undergraduate level. I think it's pretty much sufficient. So in residual analysis, what we do is, it's not something very much out of this sort as you are going to see. It's going to be very easy. We just construct the model, and then you check the significance of regression. Well, actually, it's not related to residual analysis, but this is the very first thing that you should always do. You have a first order model, you assume a first order model, you have experimental data, you fit your data to the model, then the first thing that you should do is check whether the model is significant. This is not related to anything related to residual analysis, but this should be the very first basic step to make sure that you do not fit the noise, but there is really a relationship between the response variable in the y-axis, on the y-axis, and the independent variable or covariate or predictor variable on the x-axis. Once you make sure that your regression is significant, the next step would be find the residuals and then check whether there's a trend. So this is the novel part of this presentation. So a typical example, let's say that we have some pressure versus temperature graph of anything that you would like to imagine, and it is consists of these experimental points. And what we do is we don't have any, let's say, theoretical expectation about this relation, but well, we have some theoretical expectation. Of course, it depends on the process, but we know that they are dependent on each other. When temperature increases, pressure is likely to increase. But of course, depending if you have a closed loop system or something like this, things may change. But the first thing that comes in mind is if temperature increases, pressure increases, which seems to be validated by this experimental data. Anyway, so we start with a first order model because we start with the simplest model at hand. And model 1 gives you this result. This 81 minus 81.9 is the intercept, and 217 is the slope. So it's 217 times temperature. This plus minus quantity I written in parentheses corresponds to 95% confidence interval. So using this 95% confidence interval, you add and subtract this number from the estimated value of beta 1. You may come up with whether your regression is significant or not. For those who would like to understand this, actually, I think most of you have, but just go back to your statistics textbook or statistics notes. Anyway, so once we find that this regression is significant, what we do is we may draw, if we have a simple linear regression model such as this one, it's a very good idea to show on the experimental data the theoretical response or this expected response or the estimated response of pressure here. So this line corresponds to minus 81.9 plus 0.217 times the diagram or figure I made. Now, what we call residual is the real value at any temperature, which is, for instance, around 200 here, and at the same value, the estimated value, which is about 160. So therefore, for this temperature value, whatever it is, let's say it's 200 or 300 Kelvin. So for 300 Kelvin, let's say the residual is going to be equal to 200 minus 160, which is going to be 40. And it's, as you can see, it's here 40, this value. And this value is going to be, so that's basically the distance from this point to this line along a temperature. Because as you can, I think most of you can, easily see that there seems to be a trend along these residual points. You may say, what's the big deal about that? So here is the big deal. Now, if you can see a trend, and let me try to clarify a little bit that concept of trend. That trend is going to correspond to something that you can approximate using a low order polynomial. Maybe a second one, maybe a third one at most, third order polynomial, or usually it's going to be a second order polynomial. Anyway, so if you can see a trend, so what's the big deal? So the next is, for this slide is going to be about totally about the logic if you have taken that course. So at the very beginning, we have started with this assumption. This is our assumed model. And in this assumed model, not only the form of the model is assumed, within that assumption package, there was something else. It was something about this error here. We assume that error is random, which means that we cannot predict the error value before the experiment. In other words, given the previous error values, you cannot predict the future error value. Random means this one. So it is important to, well, again, the concept of random is not that much straightforward or easy to understand, but again, for the level of this course, we can say that given the previous information about the system, all the x values, all the y values, and let's say that you can also find the error values here, you cannot estimate or predict the next error value. Let's go one step further. Once you have your models, each residual term are the estimated values of error terms. So now here comes the Shyamalan kind of twist in his movies, like Sixth Sense, not that much of a twist. Anyway, now when we have a trend in the residuals, and since residuals are the estimations of error terms, it means that errors have the error terms have trends. What does trend mean? If you know one value, you can estimate the another value. Depending on where you conduct your experiment with respect to temperature, you can estimate the random error term. But the result, the first assumption was we cannot estimate this error. However, our model says that yes, you can. Therefore, there is an inconsistency with the model assumption and with the data. Therefore, this model is invalid. Well, if you find this logical approach a little bit too confusing, you can think about statistical terms. It means that there is bias in our assumed model. What do I mean by that? Let's go back to our model here. It means this. When you conduct your experiment around 1000 Kelvin, let's say that around something like 500 to 500 Kelvin, your estimations are going to be usually above the experimental ones. So note that when I say usually above, it means this is not random error, but this is bias. So there's a systematic error here. So the systematic error is not in the equipment. Systematic error is not in the experimenter, but the systematic error is in the model. Or in the assumed model. Or when you conduct your experiment below 500 or above 1600 Celsius, your predicted values will be systematically below your experimental values. Again, there's going to be a bias, and this bias is not related to the equipment. Quite possibly, let's say it's not related with the equipment, but it may be also so, but let's say for the time being, this has got nothing to do with the equipment, so therefore it's going to be related with the assumed model. So finding a trend in the residuals shows that our assumed model at the very beginning is invalid. So what do? We just make the model a little bit complicated. And in polynomial family, a little bit complicated means make the equation increase the order of the polynomial by 1. So what we do is we increase the model order, polynomial order to 2. When you do that, you have beta 0, beta 1 times t, beta 2 times t square. I have also put here the 95% confidence interval values for beta 1, which shows that, I'm sorry, beta 2 or beta 1, whatever you would like to call this. This actually shows that this is quite possibly different from 0. So when you do that, and when you draw this diagram, and when you plot residues, note that you do not need to draw the pitted line on these points to show the residues, but this looks nice or to understand the whole thing. And when you plot the residues with respect to temperature, you can see that they seem to be pretty much random. Now, again, for those who would like to see a trend here, you may pass a very high order polynomial along or just go through these points, right? But as I said, usually when I say trend, I'm going to refer to a low order polynomial, maybe up at most third order, something like this. So one cannot say that there is a definite bias here. One cannot say that at a certain temperature range, we got positive bias in predictions. At a certain temperature range, we got negative bias in our predictions. We cannot say anything like that. Therefore, residuals do not show a trend. Therefore, bias eliminated and the assumed model is acceptable. Now, the very important point here, once you reach a model showing a residual analysis, or residuals, and by the way, this is the whole thing was residual analysis. If you obtain a residuals showing no trend, you stop at that polynomial order. You do not increase it by any more order. This is the heart of the whole topic. So in residual analysis, do the residual analysis, stop where you do not see the trend in residues. That model is valid or assumed to be acceptable. It doesn't mean it is a true model in the future. It may be cases where the model is going to fail, and probably it's going to be, but that's out of the scope of your current experiment, because the aim is for the current experiment, you would like to come up with an equation. It's not your job or your task to come up with an equation that's going to be applicable for the whole universe or things like that. It's a much more modest aim. So what is the relation of this whole thing with R-square? Now, if you just go back to the textbook explanation of R-square, basically it is a ratio, or it is 1 minus a ratio of residuals divided by the variation of the response variable. So in other terms, we can say that R-square actually shows how much variance of change in Y can be explained by our linear regression model. This part is this numerator is the part that cannot be explained by the model, because this is sum of square of residuals. So if you divide it by the total change, total variation, and if you subtract it from 1, you can find how much change or variation in the response variable can be explained by our model or by our independent variables. This is what R-square is mathematically. And again, mathematically, R-square is going to be always between 0 and 1. And again, mathematically, R-square is equal to 1 or close to 1, shows that we have a very good fit. But really, what does R-square show? Or what does a good or a poor fit mean? Now, this part, as I also said in my online presentation, is a little bit far from complete treatment of R-square or the approach. It is correct under some conditions, but it's not going to be a total treatment. But as I said previously, this is the best that we can do for the time being. So if the model is true, R-square is a measure of the precision of the model. What do I mean by that? To show the whole thing, I'm going to give you 3 different sets of experiments. These 3 different sets of experiments have been conducted on the same reactor, let's say. And in this reactor, we take concentration versus temperature measurements. So in the same reactor, we should realize that the same relation should be valid, or let's say that somehow steady state conditions are assumed. So the same relation between concentration and temperature will be valid or will be maintained for these three different experiments. So what's the difference between these three different experiments? In these experiments, the first experiments correspond to a set of experiments conducted by inexperienced practitioners with poor equipment, whereas the third set of experiments have been conducted by very experienced practitioners or experimenters using very precise equipment. So the same system has been tested using three different groups: some inexperienced group, a very experienced group. But the natural law or the relation between concentration and temperature should be identical for these three cases, because the process is still constant. It's the same process. So therefore, using this logic, we should realize that the same model is going to be applicable for these three cases. So I have produced this data using MATLAB, and I have used the same model there, producing this data. And really, it seems a linear fit seems to be valid for these three cases. So although the same fit, the same first order fit seems to be valid for these three cases, what is the difference between those three? The difference is the inexperienced case, the imprecise measurement case, correspond to scattered data around the well fit, whereas the experienced, the precise measurements corresponds to a small scattered amount of scattered around the fit. So R-square is basically related to this amount of scattered if the model is true. So you should understand this idea. So this automatically, actually, logically, next step would be, if you have this data collected from these inexperienced users, you cannot do anything, and you should not do anything to increase the R-square of this data by any statistical trick, because this is the first order model, it is the correct model, and there should be nothing else that you can do. Anything that you can do is going to superficially increase R-square. This is the very important thing, because the data itself carries that much precision. There is not much you can do there. So this is the important point. So let's concentrate on this one. Let's concentrate on this data. Let's say that we collected this data. What we do is we assume a first order polynomial model here. This is our first order polynomial model. I check the p-value of beta 1, which is 0.005, which means that it shows that the regression is significant. There seems to be a relation between concentration and temperature. Then what we do is residual analysis, because we would like to check whether concentration versus temperature, the first order model, is sufficient or valid. So I draw the residuals. There seems to be almost no trend in residuals, but as one can see, if you try a little bit hard, you may maybe see a trend like a quadratic one here. Though it's not very well pronounced as the previous one, it still seems to be a quadratic trend. Now, for this case, it is totally coincidence. How do I know that it's coincidence? Because I have produced this data using a first order model. So how is it possible that due to coincidence, we may have a quadratic trend like this? Because we have 10 data points only. With 10 data points from time to time, maybe I should have changed the data. I should have produced another run, but that's also a good example to give you as a problematic example. If you have small number of data points, it is possible to obtain trends, although essentially there is no trend. There is not a very good method of overcoming this problem. The best way of overcoming is the experience, I may say. So for 10 data points, I would say that in order to have a definite trend, I would need to, or in order to see a trend, I would need a much more pronounced curvature. So here I do not see that much of a pronounced curvature. So I think that here first order polynomial seems to be sufficient. So you stop here, you do not increase the order. So the next step would be the report. You just report the R square value, which is 0.84 or 85. With that R square value, the person who reads your report realizes 2 points. First, there's a first order polynomial relation. Well, I tried to avoid using the linear term. Actually, first order polynomial also correspond to a linear line. On the other hand, in linear regression, since we use the word linear for parameters, there may be a confusion. So I prefer to use first order model. Anyway, so there's a first order polynomial relation between temperature and concentration. And the second thing is, there is some imprecision in your model. So you do not expect to obtain, given a temperature value, you do not expect that concentration will fall exactly on the line, but it's going to be scattered around the line for some amount, because R square value is something like 0.8, which means it's a moderate fit, but there is not anything that you can do statistically. Then you interpret and use your obtained formula for predictions or whatever you would like. Now the incorrect next step. You find this 0.84, 85 insufficient for the assistant or for the instructor who's going to read your report and say that let's increase this R square value, our model will be better. This is incorrect. So if you do that, so this is our first order model. If you increase the order of your model, make it second order, R square increases to 0.88. Now, this seems like a good thing, but actually it is a superficial increase. You just increase the order, although essentially the first order model explained this just because of mathematics. There is nothing physical going on here. You increase the order and R square increases. And how is this possible? It is due to now we have an additional flexibility. Let's only think about geometrical terms. When you have a linear line, it is just there. You cannot make a curvature. Now you have the right to make it into a curvature, right? What this system has done is it has taken this part here and increased it here. So there's a curvature and it's a better fit. So the errors have been, the residues have been decreased. When you increase a third order, up to a third order polynomial, now you have you may have a maximum and a minimum. Note that here for a second order polynomial, you have a single minimum. For a third order polynomial, you are going to have a minimum here and also a maximum somewhere here, which is beyond the border of the presentation. So what is the advantage of that? It makes another curve here, right? So this may increase faster, then it may decrease here, so to pass through this point. So the fitting error is smaller, R square is higher. And with the fourth order, you have more of these different, the changing slopes, I may say. And as you increase the order, it increases more, increases sixth order. Actually, R square is still increased, but we cannot see it because it is in the least significant figures. So what I'm suggesting here is, this does not mean that our model is better. Our model is essentially a first order model because I have produced data that way. But even though the true model is first order, and when you produce data using a first order model, by just increasing the order of your polynomial, you artificially increase R square and you get the false feeling that your model is better. It is not. You may say that, so okay, but maybe it's not an advantage, but increasing R square and having a fifth order, sixth order model, is it bad? Yes, it is. I'm not going to talk about the details about that. It is a little bit related to statistical learning concept. But anyway, so stopping at the smallest order is not only for having the smallest model and a modest and smallest model, but also again for statistical purposes, it is important. Let me give you a hint. If you are going to use it for predictive purposes, then your first order model will be the best, believe it or not, compared to, for instance, this sixth order model. just assume that you conduct an experiment at 70, right? This is what your assumed model suggests, which is going to be something like 2, right? And this is going to be, believe me, the very much closer to the true value. Compare it with this one, around 70. This says it is around 4. 2, well, actually we cannot see here 2, but this says 4. As you can see, the range here, y-axis, are not identical. So this value that you can see is much higher compared to first order model. As you increase the model order, you have much a faster increasing and decreasing curves, which is pretty much problematic for predictive purposes. So the moral of the story is, once you assume a functional form of your model, what we use and do the significance of model check, then you use residual analysis. If the residuals do not show a trend, that's great. This is your valid model. If it's not, increase the model order, bye-bye. Once you determine a valid order using a residual analysis, now report your R-square value. That's where R-square plays a role. Looking at the R-square value, the reader may have an idea about the precision of your model. And do not use R-square in selecting the model order. That's the moral of the whole presentation is about, because mathematically, R-square value is a non-decreasing function of model order. So as you increase the model order, R-square will automatically increase. It will give you the false impression that your model gets better. It's not. So basically, this was the whole presentation I would like to make about R-square and choosing the correct model order. As I said, I don't know, there's going to be more of these presentations. Maybe I'm going to post a couple of offline ones. Maybe I'm going to do a couple of online ones. I don't know. But anyway, see you.